Hello everybody and welcome to this Easy 11 Plus live lesson on the surface area and volume of cubes and cuboids, which is quite a specific topic, but it's something that loads of people actually have asked me to cover in these videos. Don't forget that Easy 11 Plus is live every Tuesday evening at 6 o'clock on Facebook and on this YouTube channel. And, what's the other thing I was going to say? Oh yeah. And don't forget to like, subscribe and click the bell button. If I've watched my own videos, I'd know to say that. And finally, don't forget that there are loads of useful links in the video description, which is down here on YouTube and up here on Facebook. And those links include lots of free resources that you can download and use right now in your 11 Plus practice. Right, so today we're looking at maths. Fun, fun, fun. You've seen the worksheet already, I'm sure. If not, it's linked in the video description, and I strongly recommend having a go at the questions before you watch the rest of this lesson. It makes these lessons much more useful, in my opinion, if you've already at least had a try at the worksheet. And without any more ado, let's get started. So, this is just a simple question to get us started with a bit of a sense of what we're doing with volume. So a cube has side lengths of 1 meter. It's always a good idea when you're dealing with questions about 3D figures, that kind of thing, to sketch them out. And 3D sketching is dead easy if you just treat it if you don't take it too seriously. Do something like this. So here's a square, honest, it's a square, and here I am turning it into a 3D cube. Look. And it's got length 1, 1, 1. Yes, you could put meters, but this is not a sketch for anybody else. This is just a sketch for me to help me with my working as I answer a question. So I could just put 1. Now this is our cube, which has got 1 meter by 1 meter by 1 meter. So that means I find the volume by doing 1 times 1 times 1, which equals, no surprise, 1. So the volume of the cube is 1 meter cubed. Okay, really simple. It's just a warm-up to get you thinking about it. Now, what do we mean by volume? We mean how many cubic meters can we fit into this cube? And of course, we can fit 1 cubic meter into a cubic meter. No surprise. But it's just a warm-up to get us thinking about volume. Now, pushing on. What is the volume of the cube in centimeters cubed? Ah, yes, of course. So this is 1 meter cubed. So therefore, of course, there are 100 centimeters in a meter, so it must be 100 centimeters cubed, right? I wish the comments were in real time and not about 30 seconds delayed as they are, so I could see your reaction to this, because this is the wrong answer. 1 meter may be 100 centimeters, but 1 meter cubed is not 100 centimeters cubed. Why not? Well, a meter is something like, I can just about fit that on the screen. It's something like that. And the height can be something like that. And the depth something like that. It's a big box. 1 centimeters cubed is something like that. Are you saying that there are only 100 of these in that massive box? I don't think so. Let's work it out. So let's sketch our cube again really quickly. Oops. So if I move this around, the connection goes a bit loose. So here's our box again. Okay. Now instead of 1 times 1 times 1, now we're doing 100 times 100 times 100. Okay? It's 100 centimeters in each direction because there are 100 centimeters in a meter. What's 100 times 100 times 100? Shouldn't get too far from the mic. I go out and in like this, and my voice must sound extraordinary. Well, we've got 1, 2, 3, 4, 5, 6 zeros. So it's 1 and 6 zeros. So it is, as some people have correctly put in the comments, 1 million centimeters cubed. I love watching all the comments and all those people who think that I really thought the answer was 100 centimeters cubed, who are going, no, it's incorrect, it's a mistake, big mistake. I love this one, especially from Mohammed. How, Robert? He's written. Well, I do make mistakes all the time, but not that one. That would have been a cracker. corker of a mistake. No, it's 1,000,000 centimeters cubed. 100 times 100 times 100. And that's something to think about. If you ever need to visualize how big a million is, how big it is, but also how not big it is in a certain way, imagine a box which is 1 meter on each side. And in that box, you can get 1,000,000 1 centimeter sugar cubes. And that's what 1,000,000 is. Nice to have that image to think of. Okay, pushing on. So now applying this, a cuboid has a volume of 5.5 meters cubed. What's its volume in centimeters cubed? So 1 meter cubed, is 1,000,000. Whoa. Don't join up when you're doing zeros. Goodness me, that's the messiest thing ever. Equals 1,000,000 centimeters cubed. So 5.5 ... is therefore 5.5 meters cubed equals 5,500,000. Have you got that? Yep. 5,500,000 centimeters cubed. By the way, whether you put the comma separators in when you're doing big numbers, it's completely up to you. I think it can help to make sure that you see how it's broken down, to make sure you haven't made a mistake, put the wrong number of zeros. It makes them easier to read because you actually say another word wherever there's a comma. So reading this, you go 5,500,000 centimeters cubed. So the commas denote other words that creep in, and they're useful for that, but they don't matter. Main thing is don't make them accidentally look like decimal points. By the way, for people coming from European countries, maths can get confusing because these things are the other way around. So if they wanted to write 5.2, they would generally write that in most European countries like this. And if they wanted to do what we've just done here, they'd use dots. 5.500 ... to do the same kind of job. So these things can get really confusing when you cross the channel. Okay, right, pushing on. Now we get into some actual maths. Okay, people are still writing how. If you don't tell me what you're unsure about, I cannot help you. Right, anyway, what are they putting? How about? Yep, I have to make sure I hadn't made some terrible mistake there. Well, if I have, I don't know what it is. Okay, next one. So we've got a water tank in the shape of a cuboid. What's the volume of the water tank measured in centimeters cubed? Now we could sketch the water tank, but look, we're just finding the volume. We know how to do that. The main thing is to turn these side lengths into centimeters cubed. Why? Well, if we work out the answer in meters, then we've got to times it by 1,000,000, and in meters cubed, so we've got to times it by 1,000,000, and could get fiddly. Easy just to solve it in centimeters from the beginning. 3 meters 20 centimeters is 320 centimeters, 1 meter 50, of course 150, and 2 meters 200. Okay, so we have to work out 320 times 150 times 200. Now look, you can do all this as multiplications, but you've got some quite big long multiplications here. I think we can do something to make this simpler. We've got a lot of noughts here, 1, 2, 3, 4 noughts. So this is the same as 32 times 15 times 2 times, what are 4 noughts? 1 and 4 noughts. Look, just like that, times 10,000. So 320 times, so what we've done, we've counted the zeros. 1 0, 2 0, 3 4 zeros. I'm going to get rid of those to make sure the dots don't look like decimals. And 4 zeros, adding 4 zeros in is the same as timesing by 1 and 4 zeros, which happens to be 10,000, but the main thing is that it's 1 and 4 zeros. Okay, how do we work this out? So 15 times 2 is 30. So I'm just simplifying at each stage, making things easier for myself at each stage. 32 times 30 times 10,000. Okay, let's quickly work out 32 times 30. 32 times 30, ho-hum. 0 times 2 is 0, 0 times 3 is 0. Goodness me, it's tricky math. Second line starts with 0. 3 times 2 is 6. 3 times 2 is 9. Okay, so we got 960 equals 960 times 10,000. And remember, the times 10,000 is just to add 4 zeros on. So the answer is going to be, unsurprisingly, 960 and another 1, 2, 3, 4 zeros. So that's 9,600,000 centimeters cubed. Never forget the units, although for this question they've actually given us the units, so it isn't a concern. Loads of people writing the correct answer in the comments. That's absolutely fantastic. Well done. Really impressive. And Amani saying, I already know how to do this. Brilliant. I'm very pleased for you. That's fantastic. Right, next one. Okay. Converting from centimeters cubed to liters is dead easy. 1,000 centimeters cubed equals 1 liter. Okay? And if you know that, really simple. 1 centimeter cubed equals, what does that equal? It equals 1 milliliter. Of course it does. So these are really basic, really important things to remember. Another thing very useful to know, which is important later on, is, not at 11 plus, I should say, is that 1 centimeter cubed of water, 1 milliliter of water, will have a mass, could say a weight in Earth contexts, of roughly 1 gram. And that's very, very, very useful to know. Okay, anyway, so 9,600,000 centimeters cubed. So we got 9,600, I don't know why I've left so much space, and that is a 9, not a 4, litres. Simple as that. Just divide by 1,000. How do you divide by 1,000? You take off 3 zeros, which is what I've done here. Dead simple. Right, let's power on. Because we've got some trickier questions later, so I just want to get through these easier questions, which are still sort of warm-ups, just giving you the idea. Now, I said this was about volume and surface area. This one is slightly different, but it's just covering something else that might turn up, because it did in this question from Bancroft's school. So we got a cube here. We don't need to sketch a new cube. They've given us a cube. Total length of the edges, so here are the edges, things like this and this, is 240 centimeters. What's the length of one edge? Now we know it's a cube, which means that all the edges are going to be the same length, which is what makes it simple. We just need to know how many edges there are. So on the front here, there are 1, 2, 3, 4. They're going to be the same number on the back, round here, 1, 2, and then behind, 3, 4. And then last of all, we got these connectors, 1, 2, 3, and another one hidden away there. It's 3 lots of 4. 3 times 4 equals 12. So we just need to divide 240 by 12 to get our answer. 240 divided by 12 equals, let's simplify it a bit just to make it nice and easy. So it's 100 and, whoops, this doesn't work. 120 divided by 6 equals 60 divided by 3 equals 20 centimeters. There we are. Simple as that. Really easy question, I think, but it's just to get you thinking about the different things we've dealt with. Volume, now we're dealing with lengths of edges. And now on to a, what you might call a proper question, where you have to really apply your maths to do something a little bit more challenging. So here's an example of a cuboid. Now there's an important lesson in this question, which is always read the information thoroughly and don't just skip through it. So this question says the solutions to this question only require the use of integers, and it explains what those are, whole numbers. And that's a really important fact here, because if the question could allow you to use decimals, then you'd have a whole range of possibilities, and by decimals I just mean fractions of whole numbers, however you express those, decimals, fractions, whatever. You'd have a whole range of possibilities, whereas this makes it much more straightforward. Now, this may look like a horrible question. If you haven't worked out the answer yourself, I hope you'll be pleasantly surprised by how straightforward this becomes when you just approach it systematically. Now, this cuboid has faces, okay? So here's a face, here's a face, here's a face, here's a face as well, but we're not talking about that kind of face. Can't believe I've said that. That's so unfunny. I apologize. It's got faces with these areas. Now, you should be able to see with virtual certainty that the 6 centimeter squared face is going to be this one. And then one of these is bigger than the other. One's 10, one's 15. It doesn't matter, it depends where you've turned it, but let's just arbitrarily say that this one faces an area of 15 centimeters squared. This is an area of 10 centimeters squared. Again, I'm not bothering to write centimeters squared because these are just notes for me. Imagine you aren't there in an exam, nobody else needs to see this stuff, and I can't really fit in centimeters squared easily here anyway. I'll go on, I'll do it, just to make life easier for you so you can understand what I'm doing. There we are, I'm nice. Okay, so here's an example of a cuboid. Now there's an important lesson in this question, which is always read the information thoroughly and don't just skip through it. So this question says the solutions to this question only require the use of integers, and it explains what those are, whole numbers. And that's a really important fact here, because if the question could allow you to use decimals, then you'd have a whole range of possibilities, and Now, to find the volume of this cuboid, we need to know what the width, height, and depth are. You call the width, you call it length as well if you wanted to. You can call it anything you want to, A, B, C. And to find these, well, what are we going to do? Well, this face here, the smallest one, which is 6 centimeters squared, how do you get that area? Well, you get it by timesing the depth by the height. Okay, something times something is 6. What can we times together to get 6? 6 equals, well, it's 6 times 1, or 3 times 2. And in terms of whole numbers, that's it. I mean, you can do it the other way around, 1 times 6, 2 times 3, but there aren't any other options. Okay? So it could be that one side is 6 centimetres and one side is 1 centimetre. That would give us an area of 6 centimetres squared. But 6 times what gives us 15? Nothing in whole numbers, so it can't be that. Okay, it must be the other one. It must be 3 times 2. Okay, 2 times 3. 2 times what gives us 15 centimetres squared? Nothing in whole numbers, 7.5, but that isn't an integer, it isn't a whole number. Try it the other way around. 3 times 2. 3 times what gives us 15? 3 times 5. Okay, so that means this must be 5 as well. 2 times 5 gives us what? Gives us 10. This works. So this works for the areas of all the faces. Well done to everyone who says they did it ages ago. Fantastic. Well, if you find this so easy, why are you watching? Go and do something else that's more useful for you. But there are other people who will really benefit from this. Come on, don't be all stick in the muds. So we've got these lengths. So from these, we can get the volume quite simply. So we can see that it's 5 times 3 times 2. 5 times 3 is 15. 15 times 2 is 30 centimetres. Centimetres what? Centimetres cubed, of course it is. And that's how you do it. It's actually quite straightforward once you just follow it through logically like that. You could have started with a different face. So rather than looking at the 6, you could have started with the 15. You could have said that 15 is 1 times 15 or 5 times 3, but it isn't anything else. There's another way to get 15. And again, you could have tried those options. Well, look, it was kind of obviously going to be 5 times 3, and then you just need to get the side lengths the right way around, match up with the other faces, and voila, the answer pops out. Okay, a different cuboid, so let's sketch it quickly. Again, my masterful sketching comes into play. Ho, ho, ho. There we are. Isn't that a beautiful cuboid? Nothing's going to get out down there, honestly. Right, it's got side with perimeters of 30, 26, and 8. What is the volume of the cuboid? Okay, a little bit trickier. Well, look, if I'm looking at 30 or 26 centimetres, there are loads of ways to make those perimeters. I could have 10, 10, 5, 5 for the 30. I could have 8, 8, 7, 7. There are loads of different things I could do. With the 8, not so much. How many ways to get a perimeter of 8? Well, I could do 2, 2, 2, 2. Okay, that could give me... Oh, no, I'm not talking about area, sorry, I'm talking about perimeter. Can be a perimeter of 8. So then that would be 2 and 2. And let's say this was 26 all the way around. So if that's 2 and 2, that's 4. So 22, and that would be 11, and that would be 11. Okay. Then this is 2, and this is 2, and this is 11, and this is 11. So this is also going to be 26. So I can't have 26 and 30. So that doesn't work. Look, oops, I know I'm going quickly on this, by the way. But you can always pause the video and rewind. You can even do that if you're watching live. Actually, it works. Just rewind the video, and you can hear all that I said once more. So it doesn't work if we try to make 8 by having 2, 2, 2, 2, because then the other faces don't have the right perimeters. Okay, how else can we make 8? We can do it by having 8, 0, 0, 0. No, of course not. You can't have sides. You can't have these edges with lengths of 0. How else can we do it? We can do it with 3, 3, 1, 1. 3 plus 1 is 4, plus 1 is 4. Okay, so that's 3 and that's 3, and that's 1 and that's 1. So if that's 1 and that's 1, let's say the top here needs to be 26. So that leaves us with 24. Half of 24 is 12. Okay, and 12. Okay, if that's 12 and this is 12. So we got 12 and 12 is 24 plus 3 plus 3, which is 6. 24 plus 6 is 30. So we got a perimeter of 26. We got a perimeter of 30. And we got a perimeter of 8. And look, we've solved it. well, pretty much. So we found that this cuboid is 12 times 3 times 1, okay, which gives us 12 times 3, of course, is 36, and times 1 is still 36. So we've got 36 centimeters cubed. So again, it's just a matter of sensibly trying options. But the really important thing here was to start with the side with a perimeter of 8. Perimeter, distance around the outside, side or face, I suppose you call it, to be more mathematical about it, because there aren't many options for getting a perimeter that adds up to 8. You can have 2, 2, 2, 2, or 1, 3, 1, 3. There aren't any other whole number options to do that, so it's pretty easy to try those and get the answer. Okay, someone is saying that it's laggy. It might be laggy. My internet is rubbish this week. I don't know why, so I apologise if that's the case. There's nothing I can do about it. Right, I appreciate not everybody may have understood that, but I feel I need to keep moving through quickly so the lesson doesn't take forever. I would just say pause it, rewind, watch that again, and I reckon you'll probably get the hang of it the second time. Okay, next one. A box measures 20 centimetres by 11 centimetres by 15 centimetres. Look, you know how to do this. Really, it's pretty simple. So you've got 20 by 11 by 15. Timesing by 20 is really easy. Let's do 11 times 15 first of all. So yeah, let's do that. So 15 times 11. I always choose to put the small number second generally. Oh, this is really simple. So times 1 by 5 and 1 by 1, you get that, of course, and then the same thing again. You always put a naught at the right of the second line, and of course if it was the third line you put 2 noughts, you remember that. Then we add them together, we got 5, 6, 1, so we got 165. We just need to times this by 20. Let's just take a shortcut on this. So timesing by 20 is timesing by 2 and then sticking a 0 on the end. So timesing it by 2, well, 16 times 2, 32, so it's going to be 33. 33 with a 0 in the end. So 330. I know that... so what am I talking about? That's it. Not 330. Times by 2 is 330. So times by 20 is 3,300. In an exam, you wouldn't take that shortcut. You'd actually work it all out. But I'm just trying to speed on through. So that's the answer. It's that centimeters cubed. Just remember that 3,300 centimeters cubed is not 33 meters cubed, as we explained earlier, because in a cube meter there are 1,000,000 centimeters cubed. Right, and now we got the string question here. Someone actually got in touch with me the other week because they were trying to work out, they couldn't really understand this one. So this is probably worth taking the time to explain. So a string is tied around the box, and it's got a bow at the top, and the length of the bow is 8 centimeters, and we need the total length of string used. Okay, and we're ignoring things like overlaps. This is one of these mathematical questions where you kind of have to assume that there's just nothing extra, that it's all absolutely exact. What am I talking about with overlaps? No, overlaps are irrelevant. I'm talking nonsense. But it is ignoring things like twists and so on, and all the little imperfections of real life. Anyway, waffle. So we've got two kind of lots of string here. We've got the string that goes around the outside like that, and we've got the string goes around the outside like that. We've also got the bow on the top. The string that goes around the outside this way is like a rectangle that's 20 by 15. Okay, so it's 20 along and 15 up, and 20 and 15. We just need to add those together. So if we add 20 plus 20, it's 40. 15 plus 15 is another 30. So that gives us 70 centimeters. Okay, and we got another bit of string here, which is 15 up and 11 in depth. So we'll do a sketch of that. So it's kind of like this, isn't it? And that's got the box running through it like this. So it's 15 up and 11 in depth. 15 and 11. Again, we're adding those things together. 15 plus 15 is 30. 11 plus 11 is 22. 30 plus 22, of course, is going to give us 52 centimeters. And lastly, we got the little bow on top, which of what? That's not a bow. That's, I don't know. Who knows what that is? Here we are. It's better bow, which is 8 centimeters. And adding all those together, 52 plus 8, of course, is 60. 70 plus 60 gives us 130 centimeters. I shouldn't put a double line. Looks like the answer. Just put a divider. This is the answer down here. 130 centimeters. It's a simple addition. Okay. I think that's pretty straightforward. You just need to be careful and do the stages. Right, now we've got a difficult one. This is a difficult one from my RSL 11 Plus Maths book, which you can find out. You can find out more about that if you look in the links underneath this video. Anyway, right, we've got these wazoo bars. Let's look at the stuff at the top here. It's here. And it's got these dimensions. It's 13 centimeters in length. Okay, don't know where we're pretending that there's nothing at the ends to be squashed. The length is 13 centimeters. And it's 2 centimeters in height. And the depth that way is also 2 centimeters. And we have to fit these in a big packing box like this. Okay, what's the maximum number of wazoo bars that I can pack, laying them on their sides? Now, you might think that the way to solve this is to do something like this. To say, well, here's a wazoo bar. It's 13 by 2 by 2. So, 13 times 2 times 2 equals, and you do the blah, 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 blah. And then you work out the volume of this by doing 145 times 28 times 28 times 7, whatever that is. And then you say, how many times does this answer go into 145 times 28 times 7, and that will be your answer. That is an incorrect method. Okay? Don't make the mistake of doing that. Why is that an incorrect method, you may ask? Well, let's imagine, I'm going to make this up on the top of my head, actually, because I didn't think about explaining this, but it is really important. So let's say that I have got, yeah, let's say I've got a box that's 10 times 10 times 10, okay? 10 times 10 times 10. Here's my box. That is the worst drawn box ever in history. Have a prize, Robert. It's so badly drawn, I'm just going to edit it a little bit, because that's just not acceptable, is it? There we are, okay. 10 times 10 times 10. It'd be more normal to do the other 10 down here. Let's not make a complete mockery of this. Okay. And so that's got a volume of, what's 10 times 10 times 10? Well, it's 1 and 3 zeros, so it's got a volume of 1,000, let's say it's centimeters, so 1,000 centimeters cubed. 10 times 10 is 100. 100 times 10 is 1,000 centimeters cubed. Think about that. You've got a little box, it's 10, just like this. 10 times 10 times 10. You can get 1,000 centimeter cubes, 1,000 sugar cubes into it. Okay. And then someone comes along and says, I've got a pipe. Well, I've got another object that is 10 times 1 times... no, let's not do that. That's not a good example. I've got something that's 100 times 1 times 1 centimeters. How many times can I fit that in? So that's going to be 100 centimeters cubed. So really, you ought to be able to get 10 of these into that first box. Hang on a sec, this one is 100 centimeters long. You cannot fit any of them into the box. Does that make sense? So, if you've got a problem like this where you have to fit things into a box, which does turn up sometimes in exams, you can't just find the volume of one and the volume of the other and see how many times one volume goes into the other volume. It doesn't work. It's a big elephant trap that examiners tend to lay. Instead, you have to do it like this. Okay, so we got a wazoo bar and we have to fit lots of wazoos in by laying them on their side. So I'm just going to sketch a wazoo down here. It does not need to be to scale. It's just to help me to mark things on. Yeah, more like that. Thank you. This is 13 centimeters long. It's too high and it's too deep. Okay, so how many am I going to fit in this direction? So we can do a division, but actually this is quite easy just off the top of our heads. So 13 times 10 is 130, so 13 times 11 is 143, so we can get 11 in there. with 2 centimeters left over. I'm taking that note because it's going to be useful later on. Okay, how many can I fit in this direction? So this is 7 centimeters deep, and the bar is 2 centimeters deep, so I can get 3 of them in, and 1 centimeter left over. And how many can I fit in stacked up this way? Well, it's 28 centimeters high, and the bar is 2 centimeters high, so I can get 14 of them in. So how many can I get in lying on their sides? Well, I can get 11 times 3 in a layer on the base of this box, and I can repeat that layer 14 times up. So 11 times 3 times 14, 11 times 3 times 14, 11 times 3 is 33, so 33 times 14. I'm just going to work that out quickly. Times 14. 4 times 3 is 12. 4 times 3 is 12, so that's 13. Start with a 0. 1 times 3 is 1. 1 times 3 is 3. Oops, that doesn't look like a 3. Add them up. 2, 6, 4. We've got 462 times. Not centimeters cubed. It's how many wazoo bars. So the answer is just 462 that I can fit in, laying them on their sides. Next question, how many can I fit in by standing them on their ends? Okay, we're going to repeat the process, and if there's space, we're going to use the same diagram, and there is, because I'm going to use this end of the diagram to do the same job. Okay, so here's my wazoo bar, like that. It's 13 high, and it's 2 and 2. Okay, so how many can I fit in vertically? I can fit in it again twice, 26, with 2 centimeters left over. How many can I fit in this way? I can fit in 3, which is 6 centimeters, so there's 1 centimeter left over. How many can I fit in this direction? Well, it's 2 centimeters in width, that's 145 centimeters, so I get up to 144 centimeters, that's 72 times, with 1 centimeter left over. So it's 72 times 2 times, what am I doing? Hang on, am I doing some? Oh, times 3, that's it. 72 times 2 times 3, 72 times 2 times 3, if I can get that right. (72 times 2 times 3). Okay, so 72 times 2 equals 144. We actually just work that out in reverse. Times 3, let's do that quickly over here. 144 times 3. 3 times 4 is 12. 3 times 4 is 12, so 13. 3 times 1 is 3, plus 1 is 4. 432 times. Okay? It's quite simple, but you just have to be really systematic and careful about it. Okay, so that was easy, wasn't it? And now we can move on to, hang on a sec. How many can we fit in with some on their sides and some on their ends? And suddenly it's looking really, really difficult. Okay, but let's think about this. Often when you've got a part C question, you need a drink of tea. Often when you've got a part C question or whatever in a long problem like this, it means that you need to take the ideas that you've already developed and then find an intelligent way to apply them. So, what do we already know? We already know that I can, let's go back to the diagram. It's definitely a moment to really concentrate. So let's look at the left-hand side here, okay? The area with the one lying on its side. So if I lie them on their sides like this, I'm going to end up with no space at the top of the box, because if I do this 14 times, it fits in exactly. 14 times 2 is 28. At the back of the box, so going in this direction here, I'm going to be left with a big area at the back that's only 1 centimeter thick. So I can't fit any wazoo bars into that because they're 2 centimeters thick. If I go towards the end over here, so I'm looking in this direction, I can see that I've got 2 centimeters left over. Now that is thick enough for some wazoo bars, okay? So I can fit a few wazoo bars. I'm going to really graffiti this end here, but I'll rub it out in a second. So in this space here, I can fit in a layer of wazoo bars. Okay. Not very many, clearly, but that's where I can squeeze at least some wazoo bars in the other way around. Now what happens if I do it the other way? If I start by getting as many in as I can vertically and then squeeze a few extra. So here's my vertical working over here. What can we do with that? So going towards the back, again, I've got a 1 centimeter layer left all across the back. Going up, I'm going to have a 2 centimeter layer left across the top here. Okay, that's going to be quite a few. That's going to be quite a few left over. I'm going to the end over here. I'm going to have just 1 centimeter left at the left-hand end. Okay, so there's going to be more space to squeeze extra ones in than with the other method, but of course if I start with them on their ends, I start off with fewer wazoo bars. It looks like we might need to try both options very quickly. Okay, let's do that. So I'm going to do another sketch of this cuboid for us to do some working in. Right, now we've established that with the first method of laying them on their sides, we end up with an area at the end that's 2 centimeters wide, has a depth of 7 and has a height of 28. And what we're seeing is how many wazoo bars can we fit into this? Well, they are 13 in length, so we can't fit any lying in this direction. They have to be standing up on their ends. We can fit 2 standing up on their ends here. So 2 in that direction, 1, 2. Okay, and remember we can fit 3 in this direction, and we can only fit 1 across this way. It's the whole point. It's only 2 centimeters thick. So we can fit 2 times 3, that's another 6. So how many could we fit in this area lying on their sides? In fact, we've already worked this out. I've just got it written down here. I can copy it across. We got 462 in here, and we can have 3 times 2, which is 6 here. So we can have 462 plus 6 equals 468. Okay, so that's the answer, or is it? What happens if we try it the other way? If we start off by standing them on their ends. So let's do another sketch. It might need to be a tiny bit smaller because I've taken up excess of room there. But I have the power of zoom. Okay, so how many could we fit in standing them on their ends? So remember, what did we find out? We found out that if we stand them on their ends, we get... I shouldn't have zoomed quite so quickly. Right, if we stand them on their ends, like this, we're going to send them down to the end until we get only 1 centimeter left at the end, so you can't fit any there. And likewise at the back, you've only got 1 centimeter space. But at the top, you've got a 2 centimeter gap running all the way around here. Okay? So what we know, rubbing all these dots out is going to take time, let's not worry about that. But we know that we can fit in 432 in the main part of our cuboid. And we know that there's a space around here that is, what is it? Oh yeah, it's 145 by 7 by 2. And we need to fit as many as possible into there. Now we already know from our working for the first part that fitting these wazoo bars into a layer on the bottom, well, we can fit 11 in this direction and 3 in that direction. So 11 times 3 is 33. So we know that in a single layer you can fit in 33. So that means that going down here, we don't need to work this all out again. We can fit 33 in up here. 432 standing on their ends, plus 33 lying on their sides, gives us, drum roll, 465. 468 is the bigger number, so if you lay some on their sides and stand some on their ends, the best way to do that to get the most in, the most efficient method, is like this, where you have most of it filled up with wazoo bars on their sides, and then you just squeeze some in on their ends in this area here to get as many in as possible, and then you're still left with some areas of space which are only 1 centimeter thick. You can't do anything about those, but this is our most efficient packing. So the greatest number that we can fit in is 468, the meaning of the universe. Okay. On to the next and indeed final question. I hope you understood that. As I've said already, if you want to understand this better, then you can rewind this video and watch those sections again. If you want a written explanation to that question, and indeed to this one, well, you'll have to buy my RSL 11 Plus Maths book, which has got all the written working and a discussion of what's going on. Anyway, what is the total surface area painted blue? Let's read the blurb first. I find this mysterious solid object in the back of a drawer. Okay. I paint the ends A and B with red nail polish. Why I would do this to this object that I've just found in a drawer, I have absolutely no idea. What kind of lunatic am I that I just take objects from drawers and start painting them with nail polish? I have no idea. This is not explained by the question. We just have to roll with it. Just be thankful that there's a screen between you and me, so I can't do any more alarming stuff apart from maths. So I paint the rest blue, more craziness, and draw a centimetre grid on the outside of the object. Of course, that's referring to these centimetres in places like this and this. These will also be centimetre lines in real life. These things here will not be, because they're stretched. Think about it. If this is a centimetre, then this will be longer than a centimetre. Think about your triangles. But I think that's sufficiently clearly implied by the problem, even though it isn't explicitly explained, that's a tongue twister, in the question. What's the total surface area painted blue? So basically I paint everything blue apart from the endpoints A and B. They're red. Okay, so what's the total surface area painted blue? Well, the top is easy. You can see that there are 8 square centimetres there. Okay, the bottom's also pretty easy if you count it up. There are going to be 12 square centimetres. 1, 2, 3, 4, 5, 6, what am I talking about? 1, 2, 3, 4, 5, 6, 7, 8 in the first row, 8 in the back row. There are going to be 16. Okay, centimetre squared. I suppose I should make my notes clear. We need to worry about the front and the back. So the front, let's just do it like this. It's easy. We got 1, 2, 3, 4 square centimetres, 5, 6, 7, 8, 9, 10. What do we do with these half squares? Oh yeah, they're half squares. So 11, these two together make a centimetre square, a squared centimetre, and these two together make it up to 12. So we got 12 square centimetres. It's going to be the same on the back. So we've got 8 plus 16 plus 12 plus 12. Okay, 8 plus 16, 24. Oh, and 12 plus 12, also 24. Easy as that. So we must have 48 centimetres squared. And that's the answer to that. So it's fairly straightforward. It's just about breaking it down into stages. Okay, right. Come on, people, stop spamming the comments. I'm going to be finished soon with this. Just concentrate. We're almost there. What's the volume of the object? Now, there are various ways to do this, but sometimes with a maths problem, if you just look at it for a second, you'll realise there's something really, really, really simple that you can do. The front layer of cubes here, we've already counted up. It's got an area of 12 centimetres squared. That's another way of saying that this front layer, so this part kind of here, oops, not the squiggle at the end, but the rest of it, is 12 centimetres cubed. And there are 2 layers. There are 2 layers, a front layer with 12 centimetres cubed, 12 cubic centimetres, and a back layer with 12 cubic centimetres. 12 plus 12 equals 24 centimetres cubed. It's as easy as that. Yes, you can do stuff like taking this triangular section and sticking it on here so that you've got a 6 by 2 by 2 cuboid, but you don't need to bother with that. Front layer's 12, back layer's 12, bang them together and you've got 24 centimetres cubed. And that's it. And that's the answer. And it also happens to be right. Good. well, all these cuboids and things like cuboids and volumes and surface areas are driving me absolutely insane. So I'm delighted to be finished with this. Let's move on very quickly to the tip of the week. And right after this tip, oops, no, not that. What am I doing? No, we're on the tip of the week, not the questions. It's all going wrong. What I was going to say is that right after this tip, I'm going to be taking your questions. That's when I should be using the questions graphic. So you might want to think about them and start putting some of your questions in the comments now. So my tip of the week is offered with full awareness of the irony involved, and that is, if you have a problem with your handwriting that means that the examiner might actually not be able to read it, now is the time to sort it out, not when the exam is a week away. Your handwriting does not need to be beautiful and perfect, but it is really important that the examiner can read what you've written. Because if there are words there that they cannot read, they won't be able to mark them, and they might start subtracting marks for them. And similarly, if they can't tell whether you've spelt things correctly, or they can't tell, whether a number is a 1 or a 7, or something of that sort. I remember when I was at university, I was actually called in before exams by a tutor who sat me down and said, we got a real problem here, because when you go into your exams, it could be that the examiners will not be able to read what you've written. What are you going to do about this? By then, for me, it was too late. Sort this out before it's too late for you. Okay, right, let's get on to your questions. Okay, we've all been frazzled by maths, so I'm not going to hang around on the questions for too long. Someone says, can you explain the new Sutton pattern? Actually, people have just started telling me about the new Sutton pattern today, so I don't really feel that I understand it very well. So that's something I would think about and maybe come back to in the future. So maybe hold that question and ask me about it in a future lesson. Someone says, what happens when you don't have time left? When you don't have time left, what happens is you have to stop, because the examiners will be telling you to, the invigilators will be walking around the room, watching for anyone who's still holding a pen. So at that point, you have to stop. I think another question to answer, though, is what happens when you have just a couple of minutes left? Well, at that point, find a quick way to finish the question that you're on. Look back at any questions that you didn't quite finish and write something. Your best guess. Just scribble down some notes, because they might still get some marks. Check back any questions that you think were very likely wrong, and just give them a quick last check to make sure that you at least think the answers are plausible, to check that there's nothing else you might be able to squeeze in. But I think the most important thing is if you find yourself running out of time, there's a minute or two left, go to any questions where you haven't put an answer or haven't put a complete answer, and scribble some notes or jot some maths ideas or whatever it might be, depending on the style of exam. Get something in there. Malak's written, I don't understand the thumbnail of the video. What does it mean? The question's about, the video was about cuboids. It's me looking into a box, which is a cuboid, trying to work out what its volume might be. That was the idea behind it. What is 2 plus 2 Robert? Well, a Robert is obviously a different unit from a 2. So 2 plus 2 Robert is still going to be 2 plus 2 Robert. And if we don't know what a Robert is in numbers, if we don't have any value for a Robert, we can't express the answer any better than that. Thank you for that question. Do you do these lessons every day, and how long are they? No, I do these lessons every Tuesday evening at 6 o'clock in this channel. But I also post various short videos. Just go into the channel and you'll find loads of videos from previous weeks that you can watch until it's time for my next live video. How do you finish a creative writing piece in 15 minutes? Because that's the time for the CEM. That's a good question from Nipendra. Well, the CEM exam isn't asking for you to write a story. It's asking for you to write something that's usually 6 to 8 sentences. So it's about writing something that's very short, but that really shows your descriptive skills. And I think that 15 minutes is enough time to do something that's really good that's only that long. How do you improve creative writing? Well, of course, you do that by using my creative writing resources, such as the RSL Creative Writing books, possibly my 11 Plus Lifeline service. But no, I kid you, completely for free. You can download some free resources linked in the video description. And you can watch my Easy 11 Plus videos about creative writing. Just go to the Easy 11 Plus homepage on YouTube, and there's a playlist there for creative writing. I'll be adding lots more to that in the coming weeks as well. Someone says I thought it was on Wednesday. I did one lesson once on a Wednesday because there was a football match on the Tuesday, and since then everybody's been asking me why the lessons aren't on Wednesdays. They aren't on Wednesdays. They've never been on Wednesdays except for when there was football on the Tuesday. Whew, every week. Tips for NVR, somebody asks. Yeah, go to the channel and look at my videos for reasoning. They should help you. Okay, I don't want to spend too long on these questions because I think we all want a deep breath, and certainly I do after playing through so much maths. I'm just going to look to see if there are any more really useful questions come through. Is CEM harder than GL? No, it's just a different kind of grammar school format. Someone complaining about NVR. Yep, I agree. I complain about NVR as well. Verbal reasoning letter codes. Look at my video about non-verbal reasoning from a few weeks ago. It does deal with letter codes a bit. Hopefully that's a quick tip. Does the handwriting need to be clear for the teacher to read? Says Mohammed. Well, ask yourself, if the teacher cannot read the words you've written, was there any point in writing those words if only you can read them? You might as well just have held them in your head. So I think that's a self-answering question, Mohammed. VR be chillin', says Oh No. What books do you recommend? That's another question for another day. There are some really good reading lists out there, actually. If you Google for 11 plus reading lists, there are some great suggestions on the internet. You'll find some good reading lists. I haven't done one of my own yet. I'd need to give it a lot of thought. And frankly, I haven't read a lot of the books that people do recommend for your age, to be honest. Which is better, ketchup or mayo? Mayo is better. Team Easton says you finished early for once. I haven't finished yet, so hold your horses. Okay. I think that's enough, because when people are asking me whether I prefer ketchup or mayo, I feel that we're running a bit short of 11 plus questions for today. I hope that was useful. Please take a moment to check all the links in the video description. There are lots of useful things there, including many freebies. And I hope to see you back here next Tuesday evening at 6 o'clock for another Easy 11 Plus live lesson. And don't forget to like, subscribe, click the bell button, and check the other videos on the Easy 11 Plus YouTube channel. That's all from me for today. Have a wonderful week, and I'll see you for the next one.